Gliding on the ice is possible because there is little friction between the ice and the blades. So gliding is enabled by Newton's first law of motion, which states that an object in motion will stay in motion unless acted upon by an unbalanced force. When a skater is gliding uninterrupted, the free body diagram might look something like this. Of course, there's actually still a bit of friction, so if I continued gliding, eventually I'd stop. But since there's so little friction, I can glide all the way to the wall with mostly the same speed. To stop, I can generate a lot of friction by turning my blade perpendicular to the gliding direction. The friction that I generate is the unbalanced force that ends my glide. Newton's third law of motion can explain how pushes in skating work. It states that for every action, there is an equal and opposite reaction. To move, I can push backwards on the ice, and following Newton's third law, the ice pushes back at me and I move forwards. In this video, I pushed and the ice pushed back, allowing me to move forward. During all jumps in figure skating, skaters act as projectiles. Projectile motion is motion when an object is thrown into the air and the only force acting on the object is gravity. This means that the object will have vertical acceleration due to gravity, but no acceleration horizontally. This means that during a jump, the skater's body will follow a parabolic path as shown in the next video. Like all other motion, jumps follow the law of conservation of energy, which dictates that the total energy, which is the sum of the kinetic and potential energies, is always conserved. Since energy is conserved, the more kinetic energy there is before a jump, the more potential energy there will be during the jump. So if I want to jump higher, I need to have more kinetic energy before I jump, possibly just by swinging my leg faster into the jump. Spins in figure skating can be explained by the conservation of angular momentum, which is defined by this formula. Inertia is defined as the resistance of an object to changes in motion, and rotational inertia, or the moment of inertia from a point mass, is equal to m times r squared. M is the mass, while r is the perpendicular distance between the mass and the rotational axis. If the blue line is the rotational axis and the point mass is my foot, the purple line shows r. M is constant since the mass of my foot won't change. So, if r increases, I increases, and if r decreases, then I will decrease. L, or the angular momentum, has to stay constant. This means that if I increases, the angular velocity will decrease, and if I decreases, angular velocity will increase. This means that if the distance between the mass, say my foot, and the rotational axis increases, then the angular velocity will decrease and I will spin slower. If the distance between the mass and the rotational axis decreases, then the angular velocity will increase and I will spin faster. And of course, a part of what makes skating so special is the falling. So I'd like to conclude with a special thanks to the force of gravity, which accelerates us towards the Earth at a rate of 9.8 meters per second squared.